Hello, welcome back to another video in this course, and we are going to continue our study about the transfer of electrons, and we're going to look specifically at the transfer of electrons with metals. We've talked before about ionic compounds, and ionic compounds happen because of a transfer of electrons. That electrons go from the metal to the nonmetal. The metal, therefore, is going to have a positive charge, positive 1, positive 2, positive 3, depending on how many electrons it gains or loses. And then the nonmetal is going to have a negative charge, negative 1, negative 2, negative 3, depending on how many electrons it gains. So we've talked about the transfer of electrons before in reference to ionic compounds. So metals are the ones that are going to lose electrons and become positively charged. Nonmetals are going to be the ones that are going to gain those electrons and become negatively charged. We also talked about the transfer of electrons in reference to redox reactions. Remember, redox reaction is specifically a reaction where there's a transfer of electrons. Oxidation, the oxidation part of a redox reaction is the losing of electrons. Some atoms have to lose electrons. Some particular atom, I should say, has to lose electrons. And then the reduction part of that redox reaction is the gaining of electrons. Some other atom has to gain those electrons. So we're going to dive into this idea of gaining and losing electrons a little more deeply and look at metals and kind of compare them. Are there some metals that really love to lose their electrons? In other words, they lose them more easily, and others that kind of hold on, they're a little more greedy and they hold on to those electrons a little more tightly. So one of the chemical properties of metals is that they form cations, as I just mentioned right there. This requires them to lose their electrons or be oxidized. Oxidation is the losing of electrons. Electrons need to go somewhere. They don't just go out into space. So some metals will tend to stay in their neutral state, not lose their electrons at all. But other metals are better at making cations, and that's to say that they don't like to be neutral. Okay? So which metals like to stay neutral and don't like to lose their electrons, and which metals like to lose their electrons and therefore become ions and become more reactive? All right, let's look at Model 1. Model 1 is showing us 6 different situations. Oh, sorry, we have 9 different situations. And basically they're showing us, for example, in case A here, that we have a container, and then the arrow means something occurs, a reaction occurs. This container has a solution in it, and then there's a piece of metal, looks like, in there. Okay, and then something's going to occur. And that's the case in every one of these. So situation A, B, C, D, E, F, G, and H, and I, and we're going to compare basically what is happening. It says here that water molecules and spectator ions. Spectator ions are just ions that are in the solution here but are really not part of the reaction, have been left out just so that it doesn't get confusing. Okay. Which ions, sodium ion or nitrate, this is a polyatomic ion, are more likely to be missing, in other words, spectator ions, they don't write them in there, in the beakers of Model 1? Explain your reasoning. Well, let's go back up here. We're looking at the beakers in Model 1. Which ions, sodium or nitrate, are more likely to just be not written there because they are spectator ions? In all of these reactions, you'll notice that we have metals. It's a metal, this is a solid piece of metal, magnesium, and here we have a metal as an ion in solution. Here we have that magnesium metal again. Here we've got solid zinc, and there we've got magnesium ions. So anytime you see the situation where there's just kind of a solid piece or a solid deposit, that means you've got actual metal atoms that are there. If you see a charge, that means you've got ions. Okay? So this is solid. These are ions in here. You'll notice these are all metals. Well, let's go back to our question. Sodium or nitrate, which of those are metals? Sodium is a metal. So if, it's not shown, but if you did have the situation where sodium was involved in the reaction, you would see probably that reaction involved sodium as in the cases above in Model 1. But nitrate is not going to be a part of what we're testing here as far as comparing metals. It's not a metal. That is a collection of polyatomic ion that has all nonmetals. So nitrate is most likely not even going to be shown in our reaction, and it's going to be considered just a spectator ion. Examine the diagrams in Model 1. List two pieces of evidence from experiment A that indicate a reaction has occurred. Okay, well, if we look back up here, what has happened? We're just comparing, I'm going to number these here, comparing 1 and 2 in experiment A. Container 1 and 2. They're the same container, it's just time has elapsed. Time has gone by. So, what's the change? First change here is we see there's a deposit of zinc metal atoms here on this magnesium strip. And we also see that there's been an increase, or actually maybe even a total change of ions. What we used to have zinc ions in the solution, now we have mostly probably magnesium ions. So you would just simply say, two pieces of evidence, there are zinc atoms deposited. These are actual metal atoms, you would be able to see them, okay? And you have magnesium ions that are created. So you have zinc metal, solid zinc, and magnesium ions produced. Those are your products. Just a little hint. List two pieces of evidence from experiment G in Model 1 that indicate no reaction occurred. So if we go up to G, notice there's no change whatsoever. You have copper strip, still copper strip. No change here in this metal. Magnesium ions in solution, magnesium ions in solution. Okay? So there's no change in metal, copper, and no change in the solution, the ions that are in solution there, okay? Circle the letter below each experiment in Model 1 that resulted in a reaction. So let's just look at the ones that have reactions. So really we're looking for the evidence that something has changed. Something new has been produced. So B, A, C, not D, E, yes, F, and not G, not H, and not I. Write a single replacement reaction under the beakers in each experiment to illustrate the reaction. Ignore the spectator ion. So let's just make this real simple. Here's what's happening. On one side, you've got magnesium plus zinc ion. Now that zinc there, how do you get that zinc ion in there? That zinc ion is in there because you dissolved some zinc ionic compound. It could have been like zinc nitrate, for example. Maybe you took the zinc nitrate and you put it in there. So you really would see nitrate ions in here as well, but we're not drawing them. I am now, of course, but we're not drawing them. We're just going to ignore them because they're really not part of the reaction. But I'm going to put them in our equation here. I'm going to put them in the equation nitrate. Okay? This is AQ, whereas the magnesium is solid. Now the reaction occurs. What happens? The zinc and the magnesium are going to switch places. So look, some of this magnesium right here is replaced with zinc. Some of this magnesium is going to come into the solution as ions, and some of the zinc is going to go from ion and deposit itself on this piece of metal and becomes zinc metal. So this is turning into zinc solid, and now it's the magnesium in the compound, and it is dissolved in water. So it is the magnesium nitrate that you have in solution, and it's aqueous, which just means it's dissolved in water. It's ionized in water. So that's why you see the magnesium ions. We're not drawing the nitrate ions in the diagram. Okay? So this is single displacement. Zinc was in the compound, we put it into water, and we inserted magnesium, and the magnesium kicks out the zinc. And now the zinc is by itself as just a solid. And the magnesium is in the solution, or could be written as a compound here, magnesium nitrate. Okay? How about for the next one? We've got magnesium plus, and again, I'm just going to use nitrate on all of these. You're just going to see nitrate as the second part on all of these. Aluminum nitrate. There are 3 of them because that's Al3 plus. And that's going to turn into, what do we have? We have aluminum metal being formed, solid, and magnesium ions. So it must be because magnesium now is in the solution with the nitrate ions. Like that. Aqueous, AQ, solid. This is AQ. This is solid. Okay? Let's look at C. It is magnesium again. And it's going to kick out the copper, because now the copper is going to become solid and the magnesium is going into the solution with the nitrate. So we had magnesium and then copper 2 plus, so it's going to be NO3 2. This is all aqueous, solid, and it's going to form. Now the magnesium goes into the solution and the copper becomes a solid. Magnesium nitrate, AQ. The magnesium is kicking out the copper. The magnesium is kicking out the aluminum. Oops, sorry, here. Aluminum is kicking out the aluminum. So notice in all 3 cases, the magnesium says, get out of here, zinc. Get out of here, aluminum. Get out of here, copper. I am going to react. I'm going to form the compound. Okay? I'm going to be the one that loses the electrons. I'm going to be active. I'm going to be the one who is going to produce something. Okay? Let's look at all of these. This one, no reaction occurred. But let's look at this one. Aluminum, solid, comes into contact with the zinc solution. Let's just say it's zinc nitrate, AQ. And what do we have here? Yes, zinc is going to get kicked out. So the aluminum now becomes the ion, losing its electrons, becoming a compound if it is allowed to. And so we've got the aluminum nitrate and the zinc metal. Here, what about aluminum copper? Yes, the aluminum kicks out the copper. So the aluminum by itself, but now it's introduced to a copper solution. And it says, copper, get out of here. I am going to take your spot and form aluminum nitrate. And copper now is by itself. I'm not balancing all these, by the way. I'm just showing you the reaction. Down here, no reaction, no reaction, no reaction. Okay? So let's just make a little observation. Notice when magnesium was the metal, reacted, kicked out zinc. Magnesium is the metal, reacted, kicked out aluminum. Magnesium, reacted, kicked out copper. Now aluminum is the metal. It doesn't kick out magnesium because magnesium kicked out aluminum right up here in B. Aluminum will kick out zinc and it will kick out copper. And then we say copper, nope, copper doesn't kick out any of them. All right? So we did that. Circle the species in each of the reactant beakers that underwent oxidation. Oxidation is what? Oxidation is losing electrons. Well, in order to lose electrons, the oxidation number has to go up, become more positive. So it has to go from 0 to a positive cation, and that's going to happen when it's in a compound. So it is always going to be the metal that is oxidized, whose oxidation number is going to increase. So in this case, the magnesium goes from 0 and it goes up to +2. Magnesium, 0 up to +2 in the compound. The metal here, aluminum, is 0 to +3 in the compound. Aluminum is 0 to +3 in the compound, if I was to write the oxidation numbers. So in this case, circle the species, it's always going to be, by the way, the metal that is undergoing the oxidation. The oxidation number is increasing, often from 0 to then some positive value. Draw an arrow from one species in each of the reactant beakers to another species in the reactant beaker to show how the electrons were transferred. So in every case, the electrons, let's pick one here that I haven't written on too much. In this case here, it is the aluminum that is a solid metal, and then the copper that is ion that has lost its electrons. So now, in order for copper to turn back into copper metal, it has to pick up 2 electrons per atom to go from 2+ to 0. So that means the electrons are going in what direction? They're going from the solid metal to the metal ion. That's the direction of transfer of electrons. Always from the metal, the solid metal, to the metal ions that are in solution. Those metal ions pick up 2 electrons, they become neutral metal atoms, and therefore are going to no longer be ions in solution. They're just going to be neutral, and they're going to start depositing themselves on the copper. So when a copper ion bumps into aluminum, there's going to be a transfer of electrons. They have to touch each other. They have to bump into each other, and then the aluminum says, here, take my 2 electrons, and now I'm going to go into a solution as aluminum, and you stay here where I was and take my place, and that's why you get a bunch of copper that is forming on the metal there, okay? So basically they switch places after they've switched electrons. The aluminum gives up electrons, the copper takes those electrons, the copper turns into the solid metal, and the aluminum goes into solution after the transfer of electrons. Always from the solid metal to the metal ion, that's the direction of the transfer of electrons. Okay? Find the 2 experiments in Model 1 that involve aluminum and magnesium. Will aluminum give its electrons to magnesium? All right? So aluminum and magnesium. Will aluminum give it to magnesium, or will magnesium give it to aluminum? So basically we're comparing B and D. So you can see in one case, in one direction, B here, magnesium, does it give electrons to aluminum? Yes, because a reaction occurs. The electrons are going to go from magnesium to the aluminum. If that's the case, the other direction is not going to occur. It's only going to happen in one direction when you compare 2 metals. So notice down here, aluminum, will aluminum give its electrons to magnesium? No, that's not going to occur. Okay, so we've already established that magnesium gives up its electrons to aluminum when they come into contact. Okay? No, yes. Which metal, aluminum or magnesium, is better at giving up electrons? So that would be magnesium. Find the 2 experiments in Model 1 that involve aluminum and copper. We're basically comparing them 2 by 2 here. Okay? Comparing pairs and just kind of ranking them, if you will. Aluminum and copper. So aluminum and copper here, and aluminum and copper here. So notice only one of them has a reaction. The aluminum gives up its electrons to copper. The copper will not give up its electrons to the aluminum ion. So aluminum gives up electrons to the copper. Yes, no, aluminum. Predict what might happen if you put a piece of metal in a solution of its own ion, meaning copper metal in copper ion solution, or magnesium metal in magnesium solution. Nothing. Nothing's going to happen here, okay? Because that's like your right hand giving something to your left hand, well, there's been no transfer from you to somebody else. Okay? It's not going to occur. It's like having a tug of war with somebody who is equally strong. It doesn't make sense. Okay? So nothing's going to occur if a metal is introduced to its metal, its ion of the same metal. There's not going to be a transfer of electrons there. So an active metal readily gives up its electrons and is oxidized. So activity is measured by how easily it gives up its electrons, and that is oxidation. There are 4 metals involved in the reactions in Model 1: magnesium, aluminum, copper, and zinc. Rank these metals from least active to most active. Most being gives up its electrons. And support your ranking with an explanation. So let's do this first. Let's do least active and most active. Let's do the 2 ends. That's, I think, is the easiest. So we have magnesium. Notice every time magnesium was introduced to a different metal's ion, zinc, aluminum, copper, it reacted every single time. Magnesium loves to give up its electrons. Loves to give up its electrons to other metals. Okay? And become more reactive. So magnesium is going to be at one end. Which of the metals didn't react at all, meaning it was not willing to leave the metal, the neutral metal atomic state, and turn into ions? Well, copper metal, did it react? No. Copper metal, did it react with aluminum? No. Did it react with zinc? No. So copper is more stable by itself, just as a metal atom, than some of the other metals. That's why, by the way, copper is used in plumbing and pipes, because it's less corrosive than some other metals. Okay? So copper is going to be your least one. Now let's find the 2 in between. Well, let's just compare. All you have to do is compare aluminum and zinc. Who gives electrons to whom? So aluminum, here's your answer. In reaction E, aluminum is going to give its electrons to zinc. And zinc becomes the metal, aluminum trades places with it and becomes the ion solution to make your aqueous compound there. Okay? So aluminum is more reactive than zinc, so that would be placed here, and zinc there. And that's all verified by the reactions that we saw in the model. Using your ranking in question 7, draw a reaction diagram like those in Model 1 for the combinations below to illustrate whether a reaction occurred or not. So all we're going to do is we are going to draw a reaction diagram and then figure out whether a reaction has occurred or not. So these are reactions that are not displayed up there in Model 1. So what if you took zinc, here let's just draw the diagram. We got our container. We've got a solution that has magnesium ions in it. And then we insert a piece of zinc metal. Over time, what are we going to see? Well, if you compare your ranking up here, zinc, is zinc more reactive than magnesium? No, magnesium is more reactive than zinc. So zinc is not going to be more readily willing to give up its electrons. Magnesium says, hey, I already gave up my electrons and I'm going to stay here. I don't want your electrons. I'd like to get rid of my electrons. Zinc is saying, fine, I prefer holding on to my electrons compared to you anyways, and I'll just stay as a metal. So there's not going to be any reaction here whatsoever. You won't see any change in this situation. Okay? So it's just going to be zinc and then magnesium here. Basically, you put that into solution and there's going to be NR stands for no reaction. Okay? And again, remember this magnesium got there because it was a compound that you dissolved in a solution. Maybe it was magnesium nitrate, as we mentioned before. Okay? Alright, now let's take zinc and let's put it in copper. Well, let's compare. Is zinc more reactive than copper? Yes, it is. So we should see a reaction here. We should see, as a result of this, when you take zinc metal and you put it in a solution that has copper ions in it, you should see over time a reaction occurring. And what will we see? We will see over time basically the zinc trading places with copper. And you're going to see copper, a deposit of copper being developed here on the zinc strip, and you're going to see more and more zinc atoms turning into ions, going into the solution as ions like that. So you're going to see a switch. The copper is going to go from ions to metal atoms, and the zinc is going to go from metal atoms, neutral atoms, into the solution as ions, because when the copper ions bump into the zinc says, here, take my electrons. You want them more badly than I do. So we're going to see this. Zinc solid plus copper ions, again, I'm not writing the non-metal part of this compound, is going to produce then zinc ions in solution and copper solid. Again, I should put AQ here and AQ here. So there's been a switch. And it's pretty obvious when you write out the equation or draw the diagram. In chemistry, we say magnesium ions replace copper ions in solution. When a reaction occurs, excuse me, using your ranking in question 7, determine which of the statements below are true and which are false. So again, let's remind ourselves of our ranking. Magnesium, more reactive than all of them, and that's because it is more likely to give up its electrons and be oxidized. It's more likely to react to form a compound or to become an ion in an aqueous solution. Magnesium ions replace aluminum ions in solution. Yes, because magnesium is more reactive than the aluminum, and then magnesium is going to go into solution and become an ion by giving up its electrons. Copper ions replace zinc ions. We'll just compare copper and zinc. Let's go up to our copper. No, copper is less reactive than zinc. So no, this is not going to occur. And then zinc ions are going to replace magnesium ions. No, magnesium, remember, was the most active of the 4 that we're comparing. So this would be a no here as well. Okay? Or I guess they want us to say true and false, but you get the idea. Okay, in Model 2, we have the activity series. The activity series shown in Model 2 to the right is ranking, like we did with just 4. Now this is ranking several metals, all the way from lithium all the way down to gold. And notice it says here that this is an activity series. That's what we're calling this, is an activity series of metals. Okay? Are the most active metals at the top or at the bottom? Explain. Well, let's look for our 4. We know we can compare 4 of these, right? Here's magnesium, here's aluminum, here's zinc, and way down here is copper. So we know that magnesium is more reactive than all of these. So the most reactive ones must be at the top, or most active. And the least ones are at the bottom, because we're comparing the 4 that we already found out about. Model 2, we did that most active and least active, so we can put least active down here. Okay? Use the activity series in Model 2 to predict whether a reaction will occur when the following reactants are mixed. All you have to do is this. If a metal is above another one, then a reaction will occur. Okay? If a metal is listed above another one on this list, then the solid metal of that particular one that's higher on this list will kick out the other one's ion that is in the solution, and will kick it out, and it will replace itself with its own ions. So, will aluminum kick out lead? Will aluminum ions want to replace lead ions? Just compare. Aluminum, and here's lead. Yes, aluminum is above lead, so reaction will occur. Aluminum will become the ion, and the lead will become the solid. This is going to be AQ. Okay? We won't worry about balancing this right now, but it's just enough to show that the aluminum is going to replace the lead ion. So it's going to have aluminum ions instead of the lead. Okay? Copper. Will copper replace iron? Just compare. Here's copper. Where's iron? Iron is above copper, so it's written here a little bit differently, but will the metal iron replace the ions of copper? Yes. Iron is above copper, so it's going to replace. So you're going to have the iron turning into the ions in solution. Let's say it's 3 plus or 2 plus, I don't know which one it is. And then it's going to be the copper that is going to become the solid. Okay? Next one. You've got gold, solid, and when they write this, here's the AQ, they put this in compound form. But remember, this actually is going to break apart in the water, and you're going to have copper ions. We really don't care about the chloride ions in the solution. It's just there to show you which compound you put into the water to make those ions. So will gold replace copper? Is gold above copper? No, gold is below copper, so this will not happen. You never can go up the list. You can never have a solid move up higher and kick out something that's higher. Okay, you can't have a gold ion kick out a copper ion. So this is not going to happen. And here's the metal. Ignore the spectator polyatomic nonmetal ion there. Just ignore the nitrate. You've got your metal potassium. That means you've got ions, AQ, it's aqueous, and there's your chromium solid. Will the solid kick out those ions? Will the solid kick out the potassium? Where's chromium? Here's chromium. But where is potassium? Potassium is higher on this list, and so you can't move up the list. That's not going to happen. Chromium solid is not going to replace and become more active or react with the nitrate when the potassium is already there. It's not going to happen. Although hydrogen is not a metal, it is included in the activity series. It's right here. That's because it often acts as a metal. Consider reactions A through C and predict whether the metal shown in each case will react with acid. Acid has H in it. If the metal will react, complete and balance the equation. So all we're looking here, look, solid, solid, solid. We're looking to see, are these metals higher on the reactivity list or the activity list than the hydrogen? If they are, then they will kick hydrogen out and release hydrogen gas in the reaction. So zinc, iron, and copper. Zinc, iron, copper. So here we've got zinc. Is it above hydrogen? Yes. Iron? Yes. But copper? No, you can't go up. You can't move upwards. So zinc is going to kick out the hydrogen. It's going to form zinc chloride, whose formula is ZnCl2, and it's going to release the hydrogen. Hydrogen is diatomic gas. This is a gas right here. And if I was to balance this, I would put a 2 in front of this. When you take zinc and you put it into hydrochloric acid, you will see hydrogen bubbles released, and you're going to have in solution then this zinc chloride aqueous solution. You're going to have zinc ions and chloride ions in solution, and hydrogen gas will escape. Same thing here. You're going to have, let's say this is going to be FeCl2, iron 2 chloride, and you're going to then release hydrogen gas, and we're going to balance this exactly the same way. Okay, this is your aqueous solution. Iron and chloride ions dissolved in water. Copper, we already established that copper cannot move up. It is not more active than hydrogen, so this is no reaction. In old westerns, okay, like western movies or whatever, in the time when the western was being expanded in the United States, we often see a desperate prospector get very excited when he sees a vein of gold in the wall of his mine. He's digging for gold. He's looking for the precious metal gold. It is true that gold, silver, and copper are typically found in nature as metals, meaning not as compounds, just as pure metals. On the other hand, potassium, calcium, and magnesium are never found as metals in nature. They are only found as ions in dissolved water or in ionic compounds in rocks. Those are called ores. Explain these observations of nature using the ideas of activity series. Well, it's simply put is that gold, silver, and copper are very inactive. They do not like to lose their electrons. They like to stay as pure metals. So they are less likely to form compounds or be dissolved in water and form ionic solutions. Whereas the other ones that were mentioned, calcium, sodium, magnesium, potassium, all of these are quite active. They prefer to use or to lose their electrons, and when they do, then they're looking to form a compound or be in an aqueous solution as an ion. So these are very reactive, and these are going to be more prevalent to form compounds or solutions. Okay? Active, not very active. Okay, extension questions. Plumbers often use a dielectric union joint to join pipes of different types. For example, copper pipes in a house might need to be joined with lead pipes in the main water supply. The dielectric union is a plastic joint which will not conduct electricity. Okay, electricity is just the flow of electrons, transfer of electrons. Propose an explanation for why a copper pipe can't simply be welded directly to a lead pipe. Let's look back at our activity series. Here's lead, here's copper. Lead is more reactive than copper. If you put the two together, lead is going to want to give its electrons to copper. And it's going to want to transfer its electrons to copper, and you're going to have a reaction. And as a result, let's say water, especially if these are water, you're going to have water passing through these pipes, then lead is going to want to give up its electrons and go into the water solution as lead ions. And as a result, you're going to start losing that lead pipe. Some of that lead pipe is going to start to disintegrate, and it's going to be turning into ions. You're going to lose that lead, those lead metal atoms into the solution of water. Okay? So basically what's happening here is you're going to have a reaction. You're going to have a reaction because you've got one metal that is more reactive than the other, and you don't want a reaction in your pipes that are carrying the water, because they're going to start to corrode, and you're going to end up having leaks and holes in your water system. Okay? Ships and recreational boats often have large chunks of zinc attached to their hulls in order to prevent corrosion or oxidation, the losing of electrons and reacting of metal parts in the hull or engine. The latter are typically made of iron. Explain why zinc is a good metal to use for this purpose. So basically they're saying iron, the ship is made of iron. But what they put on these hulls are huge chunks of zinc. Now why would they want to do that? Let's compare zinc and iron. Here's zinc, here is iron. They do not, this is their ship. The ship is made of iron. They don't want their ship to react. They don't want the ship's metal that it's made of, iron, to start to corrode and react with maybe something in the ocean, start to react with ions and other minerals that are in the ocean. So what they do is they attach huge chunks of zinc to their ship, so it is going to be the zinc that reacts, and the iron then is protected. Okay? So if anything's going to react, they're going to put something on their ship that will react more easily, more readily than the iron. So any reaction is going to happen here with the zinc instead of the iron that makes up their ship. Shown below is an activity series for nonmetals. Oh, we've only been talking about metals. Well, there also is a ranking for nonmetals because nonmetals can react, but they like to gain electrons. This ranks the ability of different nonmetals to accept electrons. And that means they are going to be what? Reduced. Here is a ranking already given to us. Most reactive, there's fluorine. Then we're going down to least reactive: chlorine, oxygen, bromine, iodine, sulfur, and phosphorus. Okay? Least reactive down there. So nonmetals, there's a ranking for them as well. And you just have to remember that nonmetals like to gain electrons. They like to be reduced. The activity of chlorine and iodine, for example, can be compared in the following reaction. This time we're looking for, it's not the metal that's going to replace another metal, it's a nonmetal that's going to replace another nonmetal. Will chlorine kick out bromine? Well, is it more active? If chlorine is higher, if we were to list these vertically, most active would go up on top, right? Most, least. So yes, chlorine is above bromine, and it is going to kick it out, and therefore this will occur, and we say spontaneously because you don't have to help it in any way. It's just going to occur and happen by itself. Okay? But this one says iodine. Will iodine kick out fluorine? Compare nonmetal to nonmetal. Iodine, no. It is lower on the list than fluorine, less active. So this will not occur. This will not be a reaction that happens on its own. Predict if the combinations of reactions A through D will result in a chemical reaction. Okay? So, will fluorine kick out, compare nonmetal to nonmetal, fluorine kick out chlorine? Yes. So that means you're going to have not sodium chloride, but you're going to have sodium fluoride, and the chlorine is going to be by itself, and chlorine is diatomic. And if we want to balance this, I need 2 chlorines on both sides. That's going to mean I need 2 sodiums on both sides, and now that gives me 2 fluorines on both sides. Will iodine, that's a solid, kick out bromine ion in solution? Is iodine more active than bromine? No, it's below it. So this is no reaction. Okay, compare nonmetal and nonmetal. We're not looking at the metal zinc. That was before. We're comparing nonmetal to nonmetal. Will oxygen kick out sulfur? Will it kick it out of that compound? Is it more reactive? Does it want to be in a compound more than the sulfur does? Compare oxygen and sulfur. Yes, oxygen is more reactive, so that means it's going to kick it out and form zinc oxide. That's the formula for zinc oxide. And then sulfur by itself, and in this case, sulfur is going to form an 8, it's sulfur 8 there. That is how it is by itself in elemental form. So to balance this, I'm going to put an 8 in front of this zinc sulfide, and I'm going to put an 8 here, and then I'm going to put a 4 there to balance it. Okay? All right, and the last one. Will chlorine kick iodide out of the solution? Will it replace it as an ion? Is it more likely to gain electrons? Is it more likely to be an ion either in solution or form a compound as in equation C here? So chlorine, is it above iodine? It is, so it is more likely to form the ion. So we're going to write chloride ion, and iodine is diatomic. So now to balance this, I need a 2 and a 2, and we're done. Okay? So just remember that comparing metals, we can compare metals and their activity, and we can compare nonmetals and their activity. How do you know which metals are more active? Which ones are more readily going to give up electrons, and nonmetals, which ones are more readily going to accept electrons? Okay? Transfer of electrons is a huge topic in chemistry, and we've seen a lot of that recently. And we will continue that in the next video as we talk about batteries. All right, we'll see you there.